Awesome. Thanks for the introduction. I guess I was confused about this, so I'll ask, which side are people supposed to sit on about the pictures and photography and everything?
On the left.
Okay.
People who don't want to be photographed should be on this side, and all the others can be here.
Okay, so I hope you all have that squared away. I guess, and the other thing is the mic. Is this good? Do I need to turn something on? Should I? This is fine? Okay, excellent. All right. Well, yeah, so I've been given the opportunity here to talk for 3 hours about visual analytics. And this is actually quite exciting for me because it's an area that is near and dear to my heart. It's my active area of research, and I really enjoy it. So talking about it is something that I really look forward to. And in thinking about this, I always like to start off with sort of goals for this talk, right? And to say, during this whole time, what I really want to do is be able to give you all the basic knowledge of a collection of topics that make up visual analytics. Now, I say basic knowledge, and a collection of maybe the subtopics is more accurate. The things you're about to see is really a condensation of topics that I know at our local university at Georgia Tech, we spread across probably 2 or 3 courses, right, that talk about the different aspects of visual analytics, of information visualization, of the cognitive aspects of data discovery and things like that. So here you're going to see a very short version of that. And then this is also exciting to me because this is the first time I get to give a talk where there's actually a coffee break in the middle of it. So we're going to see how that goes. So implicit there is for me to keep you entertained and awake enough until coffee, and then hopefully the coffee will take you all the way to the end. And in that second part, I'm also going to show some examples of tools and applications that have been developed for visual analytics that build on these principles that I'll talk about in the beginning. And hopefully, if there's time, and there should be, give you the chance to ask some questions and discuss. And I should also say that I tend to wander a lot while I talk, so I don't know how that's going to turn out with the video. And I also like to ask questions at times and engage the audience. And I've yet to come across an audience that I cannot outwait. Right? So when I ask questions and there is no answer, I have yet to find an audience that will not eventually find the urge to answer that question. Overview first, right? We're going to talk about the foundations of visual analytics. We're going to look at things like what is visual analytics, what are the definitions, what is the scope, what does it entail, and before then, even we're going to talk about why show data visually, right? We have other ways to communicate information. What are the advantages of showing data visually? We're going to talk about why it works so well, grounded in some basic things like perception, cognition, things like that. Talk about the computation a little bit, right? In visual analytics, we often integrate some sort of modeling or analytics, and talk about user interaction. And I have that in bold because, for one, it's an area that I particularly enjoy looking at, but I also think it's really the key to couple the cognitive processes of people with the computational processes of analytics. We're going to look at tasks, both high and low level, that people do with visualization and visual analytics. The high-level stuff I'll be a bit more light on because I saw we have a talk on sense-making and things like that later, so that I assume that will be covered in there. And then we'll look at a few of these applications that integrate data mining, statistics, machine learning, all of that computational horsepower, if you will, for data analysis. We're going to do demos, live demos, yes. Very risky, but we'll see how it goes. And we're also going to look at videos of some of these applications because a lot of times you don't get a good feel for it with just PowerPoint after PowerPoint that we do that. Yeah. Now there's about 180-something slides of details, so don't worry, we'll get through it. So, first things first, why do we show data visually? We're all friends here, so I think we can assume that there is data and there's lots of it, whether you call it big, large, or whatever you want. The funny story, even my cat has data about him, right? When I moved across the country recently, I took my cat with me on the airplane, and I found out in order to do that, you have to fill out some form on the Delta website about your cat's name, actually also like the salutation, which I thought was interesting. I picked doctor. And a whole bunch of other things like weight and size and color and breed and all sorts of stuff, right? And now, we made it across the country all safe and sound, but now somewhere in some, I would say, moderately maintained database of Delta, there's actually data about my cat, right? Who knows what will ultimately come of this, but needless to say, our everyday life now is generating data. I think we can think about the idea that we have sensors that siphon data and we put them there for a reason as being something that's slightly bigger than that now, right? Where we as people are actually generating data just by being in the digital age, in the digital era that we're in. And this is exciting, right? This creates new fields of study, right? Things like data science really help solidify computing as something that not only sort of teaches computer science and the principles and advances those, but also helps other disciplines do their science in more well-established fields, right? I often think about astrophysics and biology and these other things that are now really benefiting from the advances that we've made within data science and computing in general. And I know a lot of times people say the data is overwhelming and the dangers of big data and the challenges, but I really like to think about the opportunities, right? I think there's always the other side of that coin, and in visualization that's really exciting for us to look at, right? So the opportunity here comes through the approaching this challenge of how do we let people gain insight from data. We want people to make decisions based on data. I echo two of the talks this morning when I say that, right? Data-driven decisions are very important, and understanding how to integrate data into decisions that people make is really a fascinating area of visual analytics. And we oftentimes form and sometimes even change people's opinions about important issues in the presence of data. And understanding that relationship between data models and mental models is something that's really important to be able to do that. And we learn and discover new phenomena, right? And this really echoes this long standing thing from Richard Hamming here, right? The purpose of computing is insight, not numbers. And I think the same is for visualization, where we sometimes say the purpose of visualization is not pretty pictures, but it's actually to understand your data, right? So if we want to think about further formulating this, we really have this challenge of transforming data into understanding or insight, right? So if you want to think about it at a very technical level, this is actually sort of a data transfer problem, right? We've got a bunch of data stored in a database or databases, and ultimately we want to transfer that information into a person's head, right? And the question there is how, right? We can do things like verbalize the data, right? And then you use your senses of hearing to be able to do that. We can do things like potentially smelling the data and see about information that comes from that. But really, one of the high bandwidth channels that we can use is our visual channel, right? People are very good, for many reasons, at seeing things, at looking at scenes, and being able to make sense of the information they see when it's actually presented to them visually. And so this is really impressive. Therefore, that's sort of a bit of a very foundational level of why we want to use visualization, right? Human vision, it's fast, it's parallel. We'll talk about pre-attentive vision a little bit. It extends our memory and cognitive ability, right? Think about doing long division or multiplication. Oftentimes, it's easier to do if you have paper and you can write things down. And even the spatial constructs that you employ help us offload a bit of our working process onto a visual medium, even in that very fundamental example. And therefore, you know, we can use visualization in that sort of a way. So I'm going to just do a very quick, simple example here of some simple data. Here it is. It's cereals, and we have different manufacturer codes for these cereals. We have also how much fiber and how much potassium these things contain, right? And this is in a very familiar format as we look at data. It's in a spreadsheet, and I might ask such things like, what do you see as an interesting pattern here, or what do you see as a potential outlier, or do you see any errors in the data? And this is a bit of a straw man argument because this is in a format that doesn't lend itself very well to those kind of spontaneous insights or even formalized insights. Where instead, even using something as simple as a scatter plot here, right, where we can map data attributes or the dimensions of the data onto the x or y axis. So in this case, we have fiber and potassium. We've mapped color to the manufacturer codes, and we can start to see things like, for example, the blue manufacturers tend to be down in this region a bit more, and there are a few that are actually really far up there, right? And now, depending on what I'm looking for in a cereal, in my diet or whatever it may be, I can now start to understand the space of where cereals are with respect to potassium and fiber much better than I could in this kind of a table here. Right? So, this problem gets even harder, right? What if I only told you one cereal's data at a time, right? So I gave you a table before. What if I now only showed you one row in that table at a time, and they just kept getting added to it, right? Maybe in a streaming data context, for example. This is much like some websites, right, where you have to click next and tab through things to get to the data. So that actually makes this much more difficult. Also, what if I read the data to you, right? I don't show you the table, I just read it, right? And this sort of examples help motivate why showing the data and getting the overview of all the data is actually a nice way to do that. Who here has seen this? Yes, nice, almost all of you. This is a nice depiction of Napoleon's march into Russia with his army, and the width of the bar here is the army marching up all the way to Moscow and then back. And you can see as the width is getting skinnier, that his army was getting smaller. But it was really one of the motivating examples that I like to start with of saying data visualization has been around for a while, and it helps us really think about the events that happened and start to contextualize them into our own experiences of what we know about winter in Russia, or what we know about the impact that a bar that was very thick, meaning lots of people, means when that bar gets thinner and there are much fewer people, right? And our own experiences help us really think about and reflect on the data that way. There's many other examples, right? This here is another one that I frequently point to. This was a depiction of the O-ring damage through field tests that came about in the Challenger shuttle launch, right? And this is a visualization of where the O-rings failed, right? So these little these little texture boxes are actually indications of where those O-rings failed on these booster rockets. And up at the very top on the nose of the rocket, actually, you see the temperature that it was at the time of the launch, right? And this was how they showed this particular bit of information in order to present in their tests how those O-rings have failed given the temperature of the actual launch, right? So this is, the power of showing visualization well is that actually if you put it into this kind of a view here, as Tufte in many of his books articulates the value of presenting information in a meaningful visual representation, we can actually start to make decisions much better based on the data, right? So we had data that day that it would be about 26 to 29 degrees Fahrenheit at the time of the launch, and the decision had to be made whether it was safe to launch or not, right? And each dot here is an example, or is a bit of data collected from testing that points to O-ring failure at different levels and different amounts of damage, right? And so given this, one might have come to the conclusion that, one, there are no tests that have been conducted even near that temperature range, and two, it seems as though the amount of O-ring damage increases as the temperature gets lower and lower, right? Which is much harder to tell from a visualization such as this one, right? And even worse, the engineering notes, where there's actual pictures of this that were handed to the decision makers at the time. Very tabular data format, if you will. Okay, so this is a definition of visualization that I like to use. The use of computer-supported interactive visual representation data to amplify cognition. And it's really that last part that I really appreciate about this particular definition. And this is from the 1998 book from Card, Schneiderman, and others, where they sort of started to define this idea of information visualization. And like I mentioned earlier, it's often thought of as a process of making a graphic or an image. Right? You oftentimes hear things like visualization is good because it shows me the data. We often get approached as visualization researchers and practitioners with, I have a pile of data, can you visualize it for me? Right? I need to know what's in it. I have no idea. Please show it to me. And I sometimes push back on that a bit and say that it's not really all about making a single graphic or a single image, but especially in the analysis context of visualization, it's really about fostering cognitive processes. Right? It's about having us ask questions about the data that maybe we didn't know ahead of time. It's about forming a mental model of a phenomena, or seeing how your mental model of something that's happening actually maps onto the data that exists for that. It's about internalizing and understanding. And again, thinking back to that long division thing, it's really about sort of allowing you to more effectively go through that process of discovery and understanding. Right. Purpose is insight, not pictures. Right? So, main idea for Viz is, like I said, they help us think. They leverage a combination of cognition and perception. They allow us to do things we're very good at as people, like pattern matching. And they're an external cognition aid. And this is really helpful because we think and reason about the world in the presence of data on a continuously increasing basis. Right? I think it's becoming more clear that we no longer are sort of divided into times of the day where we sit down and do formal data analysis. But I think data is not only produced by us more regularly, but are also consumed by us more regularly. And therefore, it's something that really starts to become more of who we are as people as we start to think about how to use visualization, what the applications of visual analytics are, and things like that. Okay. I think it's helpful now to also walk a bit through definitions and scoping of what visual analytics is. And I'll also touch on things that I will not talk about during this talk, but at least give you the keywords or the areas or nothing else to be able to look those things up. So this was a book, which was already talked about earlier, and Chris Cook, we're lucky enough to have her in the audience as one of the editors of this book. The science of analytic reasoning facilitated by interactive visual interfaces. And I particularly enjoy the word science in there. I'm glad that made it, because it's really a discipline where there are a lot of unanswered questions. And as a group, as a community, we can both answer those questions, apply them, and adapt them onto or into domains that really have the need to understand their data like that. And it's available for download. It's actually quite a nice read in terms of the PDF. I urge you to take a look. An alternate definition, I believe came out of did this come out of a dog stool way back in the day? I don't remember. But anyway, it's in this book. Daniel Keim, as well as John Stasko, Chris North, and Jean-Daniel Paquette authored this book where they talked about information visualization and some of the futures of information visualization. And one of them came about this term visual analytics, where they said combines automated analysis techniques with interactive visualizations for effective understanding, reasoning, and decision making. Right? So really emphasizing that idea of combining things that we can automate with analysis techniques of why we need a human involved, right? To sort of balance that effort a little bit. So, at a very simple level, these are the main components of visual analytics, right? We have an interactive visualization or user interface. We have some form of computational analysis, right? Our CPU or GPU is computing something. And we have analytical reasoning, right? We have the way that we think. Pretty simple, right? Well, perhaps a bit more accurate might be this view here, where we see that the scope of visual analytics actually incorporates many disciplines and many areas, topics, keywords, buzzwords, most of which I will not talk about today, because we would be here until it is truly summer. But this is really to point out that part of what makes this exciting, and why I was really happy to hear this building of community earlier, is that there's not really a single organization or a single researcher or a single group that spans expertise across all of these areas. And therefore, really thinking about that a bit more and collaborating with others, I think, is really the way forward for visual analytics. Quick aside, I like to tell stories as well, so bear with me. We mentioned 2008 and the summer school at PNNL, and it occurred to me that was actually the time where I started my PhD at Virginia Tech with Chris North, and I got to the orientation, and he literally said, "Hey, I think you should go to this thing in Richland, Washington." And I remember thinking, as somebody who had just finished their undergrad degree then, well, first I thought the only thing it does in Washington is rain, because I thought Seattle, and that's not true. But the other thing was, what is this visual analytics thing? And I went to that summer school, and I met several of my colleagues and collaborators that I still know today. But it was really great to see that community form there, and to some extent, I guess, come full circle, because we mentioned it again today. And that was really great. So as you all are sitting here, hopefully you'll have a similar kind of experience where you just get infatuated or really intrigued with some of these questions and some of these challenges that are still existing today, right? We haven't solved this. And I think that's a point that with all of the things I'll talk about today, I should try to make clear in that sort of a way. Right. Yes, won't talk to all these, but many of the things I will talk about have ties into a lot of these particular areas. Before I go on to this, are there any questions about anything I've covered so far? Okay, good. Right, so why does visualization work so well for gaining insights from data, right? Let's peel the onion back a little bit and think a bit more deeply into the theory of what we know about perception and cognition about why this actually works so well. So our perceptual processing, or our perceptual system, there's really a lot of work there about understanding why this works better, right? And this is deep into psychology and cognitive psychology and things like that, but it's really there to help us understand why these inputs, these visual inputs, are very good for understanding data. And one of the simple models, and I'll just very quickly touch on this low-level point, comes from Colin Ware, where he suggests that there is a two-stage model. Stage one, right, this is the eyeball over here, or an icon of one. Our early stage is actually this parallel detection of color, texture, shape, features that we can very quickly see. And then our stage two is sort of this part of our visual model, or our perceptual model, that allows us to do things that require more attention and is more serial in terms of the processing. And one of the, concepts that's born out of this is this idea of pre-attentive processing. And this is interesting because it allows people to be able to see things very rapidly if designed and used appropriately. And we try to do some things pre-attentively, meaning that people can see it very quickly, and other things we do sort of in serial, where we use more of that stage two or second stage perception. So, what kind of tasks is pre-attentive processing good for? We have target detection, right? Is something there? I show you visualization. I say, does XYZ exist? And you should be able to very quickly go yes or no. Boundary detections, right? Can things be grouped together? Do clusters exist? Things like that. Counting, right? How many types of a certain thing are present? Questions like that can actually be answered if designed correctly with pre-attentive processing. So, we're going to go through a few examples. The way this is going to work is I am going to show a set of images, and I'm going to prompt you with a question. And as soon as you know the answer to the question, I want you to raise your hand, right? And I'm going to just see and look around how quickly hands go up, and this might give you an idea of how fast you, as well as others, are able to see the information and make sense of it. So, the first one is, how many threes, the number 3, are there in this particular visualization? Okay, I won't test your visual acuity down to a T here. But the point is that even in talking here, we're starting to see a few hands go up. Maybe a few guesses about, I don't know, I saw 3, but I quit after that. Right? But this does not leverage pre-attentive vision. Right? Let's try it again. All right? Aha! Hands are going up much sooner. Right? And why is that? It's because our visual system is able to pick up on the color shift that I've applied to the 3s. And actually, red and black may have not been the best one, especially on a projector with lights pointing to it. But nonetheless, you were able to make sense of that information quicker. Right? Let's try another one. So the task here is to see if a red circle is present. And again, raise your hand when you have the answer. Yes, very good, right? So this can be done rapidly, right? Pre-attentively by people. It's surrounded by other objects that we sometimes in these types of experiments call distractors, but given that shift in hue, you're actually able to pick up on this quite well. Let's do it again. All right? Determine if a red circle is present. Raise your hand when you get it. Aha, right? So it's not only hue that works for this. We can do things like shape, right, that actually pick up on that as well, even though all the points are red. One more time. We're going to mix it. Ooh, I saw a hand go up and back down. I'm not quite sure what that means, but all right. So what we see here is that this actually requires a bit more processing by the combination, again, of our perceptual and visual system in order to fully understand if something is present or not. And this is because we've now combined hue and shape, and that actually creates an effect that doesn't allow for pre-attentive vision to work as effectively as before, right? We can do other things. You don't have to raise your hand anymore, but the same kind of thought process goes through this, which is to say, is there a boundary in this display, right? And in this display of information, you can say, right, I see a clear boundary between the white points and the black points over there, but then the one closer to me, there actually is a boundary, but it's sort of this combination of black points and black squares, which make it a bit more difficult for me to actually to see those kinds of things, right? It's on the diagonal there. Another example here, we can do things like mixing hue versus shape, and we can see the boundary there pre-attentively as well. We can do other things like mixing hue and brightness, which is actually quite difficult when you try to do that, right? So there is something where the two actually confound, and it's more difficult to see. I guess what there is to say about this is you want to design some things that really make true use of our perceptual and visual system to allow people to see these kinds of things. These slides were taken from Chris Healy's website at NC State. He has an entire app that you can use on his website to be able to test yourself with this and try out different things. I encourage you to do it. It's actually kind of fun to see how fast you can get things or how fast you can't get things. So if you want to do that, please give that a shot, right? And I guess the takeaway is that certain forms lend themselves to pre-attentive processing and things like that. Any questions about pre-attentive processing? Okay. I've got a few more. Quickly just walk through these. Here's another one where we're actually looking at sort of the 3D aspect of your icons and of your glyphs that you create and being able to rotate them or invert them and what people are able to pick up from that. Here again, we have distractors versus targets and seeing just the rotation and the slight differences are actually very easy to pick up pre-attentively versus a bit more difficult down here. So this actually helps us understand the fundamentals of the glyphs that we design that encapsulate some data and what we want to be very careful of, which is if we want things to be done pre-attentively, we probably want to be aware of these kinds of effects as we design our visualizations. There's another set of guidelines that come from this German psychologist from the early 1900s, the Gestalt laws, right? The Gestalts around how we see patterns and how we perceive things. And it's actually similarly interesting to look at many examples of these. Who here has looked at these before? Nice. Okay. So I will see if I can skip over the examples more quickly, but I just want to point them out, right? So it's things like proximity. Things that are close together spatially are often perceived as being grouped together, right? We perceive groups even though there is not a true grouping defined, right? Similarity. Similar elements get grouped together based on the visual appearance, right? So if I have flags that look similar in a whole array of flags, I actually start to conceptually group those, even though there may not be that proximity metaphor applied. Connectedness. Oftentimes we perceive items to be connected, even though there may not be a uniform line that connects them. Continuity, the idea that a shape will continue when you visualize it is something that we're good at picking up on. A few more things like symmetry, closure, relative size, figure and ground, right? Here, for example, this is one of the famous examples. Do you see two faces, or do you see this candlestick holder kind of thing, right? So are you looking at the white part of the image or the black part of that image? And depending on which one you look at, that is the difference of what you see. Okay, so that gives us a very brief slice of things about our perceptual and cognitive system that really helps ground a lot of the work that we've done or the work that we do in information visualization. I want to talk a little bit now about basics of visual representation. So a lot of the glyphs that we saw there and the information that I just presented, I said things like we've mapped color to this attribute. We've mapped position of the axis onto something. And we actually have quite a bit of literature that helps us describe the effectiveness of doing different things like that. And so this idea of binding data values to visual glyphs or visual representations and then ultimately embedding those into visual metaphors actually has a lot of literature behind it to help us understand which things are most effective. Right? So a good place to start is this. This is Jacques Breton's work very, very early on about the different kinds of visual variables that we have when showing information in a chart or in a graph. And if you'd like to really also, I've written them there in English, but if you'd like to test your French, I guess you can try to map the English words to the French words from this graphic here and see things like the actual things you can map. Things like position, right? Where in space do you map things to? Things like size. How big do I make an object? And what value do I map to the size? Things like color and the way that we can perceive color in different ways. Texture. You can make things more or less shaded. Orientation, right? You can start to rotate things to mean something. And then form. You can give them a different shape, right? Triangles, squares, circles, things like that. And typically, what we do is we map a single feature of our data, or single dimension, onto one of these variables and put those into our actual visualization. And so this leads us to the question of, how many of these should we use, right? You can envision making a visualization that uses all of them, right? A scatter plot where shape means one thing, size means one thing, color means another thing, rotation means something, and this entire display will maybe look pretty complex, but as we learned from the pre-attentive processing stuff that we just went through, if you start to combine many and many of these, it actually becomes more and more difficult to understand what our actual data is that we are showing, right? And so this brings us to the challenge of we can really only show a limited amount of these, right? And that means for complex or big data, we need methods to aggregate or combine those data features, right? And even then, we may still need a bit more help, and we're going to talk about that help later when we talk about things like dimension reduction, aggregation, saliency of feature extraction, things like that. But really, this brings us to this sort of optimization function of visualization, if you will, which is to say, which features do we pick and to what what visual attributes do we map those to? That make sense so far? I see nodding heads. I'm not sure if that's a caffeine wearing off or whatever it may be. But we'll keep going here, right? So, there's actually been a study, a few now actually, not just this one, but this is one of the first ones, that studies which visual features are the best to use, right? So do I use shape or do I use size? Do I use position or do I use color? And what we see here, from top being the most effective in terms of being able to perceive the value by the visual, right? To bottom being the least effective, that there is sort of a clear dominant visual feature, and that is position, right? And for the others, it actually depends a bit on the kind of data that you're going to show, and I'm going to walk through those types of data a bit later. But for now, I think the nice thing to see is that they do vary, but there are sort of clear ones that are better than others, regardless of your data to use. I sometimes think that position, right? I like to reflect on work like this, because obviously this was like hundreds of people. It was a very controlled study, and out came these results, and there was significance about some of those differences. But I often like to sort of step back and reflect on some of this work and say, well, why is it that position worked so well for some of these things? Well, I guess this is completely my personal view on this. There's no science to back this up. But I think it's because we as people often use space in our everyday lives in order to organize our world, right? I place my phone near my car keys so I remember the two when I grab the other. I put books that are similar to each other near each other on the bookshelf. And so I think that we as people are actually just really good at using position as a means to organize our information, and perhaps as a result of that, position works so well for data visualization. I don't know. Write that down as a thought for the day. Whatever. Another one that I think warrants a bit more chatting about is color. Color is a powerful visual variable to use, but it's tricky, right? And there's a ton of work that I will not get into about color ramps, color theory, all of these types of things that basically help you decide, given your data, do I use a rainbow color map? Chances are no. Just going to go ahead and say that. But it helps us understand that for different data, we may want to use different color ramps. It's not just, oh, I need to map color to my data, and out comes a nice colorful graphic, and that's the optimal one to use, right? Things like, if there is an order to your data, use a color map that has order involved, right? Not a rainbow one, for example. If there's separation in your color ramp, right? So if you don't have a linear hue ramp from one end to the other of the data you're encoding, make sure that your data actually has that, right? Because if not, you're introducing these visual artifacts into your data that could, into your visualization that are not reflected in your data. And there are limits that we've studied about the number of items or colors people distinguish. And it's basically around the 7 to 9 number there. And given that this is sort of the quick visual analytics 101, a great place to start is Cindy Brewer's website here, Color Brewer, right? You can see that it has a whole slew of color ramps to choose from that are a great starting point. You say how many categories of data do you have, and then there's a color ramp to match it. It gives you all of the hex values of those colors, all of the things you might like. You can then import those into your tool, and I think she's done a fabulous job of putting that work out there. And that's rather old, but it's still online, and it's pretty good. I personally used it. I think it works fairly well. Again, knowing what you're trying to accomplish with your color ramp is key. I haven't looked at that site in a while, but I don't think it actually tests for some of those things. And then this recent work here, I just thought I would highlight because I found it really interesting. It was just at Viz this past year, I believe, is work that actually says, well, oftentimes the categories of our data in our visualization are things, right? And we can Google those things, particularly do a Google image search of those things, and come up with a color given all of the results that come up on Google, right? So we have things like here, carrots have this orange kind of color. We have things like corn have this yellow kind of color. And so what this technique here did was literally look at the names that you give variables, do a Google image search, pick some top amount of images, I don't quite remember, and figure out a color to give that variable. And I thought that was a clever way to say, well, color ramps map well to just the quantitative shape of your data, if you will. But a lot of times the variable names also resonate with us in terms of what we expect to see, right? Carrots being orange in this case, and things like that. Can anyone think of limitations of this kind of an approach? I've got a few, but I thought I'd ask. Yes? You first, why not?
Two things that have very similar color.
Two things that have similar color, yes, that's certainly one, because then, again, you come up with a color ramp where you can't distinguish between the two, right? If you have broccoli and lettuce, it's going to be very difficult to see, oh, is that shade of green a little bit different from this shade of green? What else? Yes?
A lot of the sort of stuff that I personally work on is security incidents, which are just going to get a brown.
That's correct. That's correct. Sorry I didn't pass the mic around, so I'll repeat the answer. It's some of the events or some of the labels to the categories may be things where the images are all very similar and maybe don't have that clear iconic color that goes with it. And that's another great example. But I thought for some things this is an interesting approach, right, to appeal more so to the personal side of what we think color of things mean. All right. At this point, we're going to talk a little bit about user interaction, right? And this is really sort of where the viz hits the person, or the person hits the viz, right? Or fighting back to some extent. And I think this is really crucial because it transforms a person from a viewer to an active participant in the data analysis process, right? No longer are you sitting back watching TV and just seeing images flicker at you. You're now in control. And you can do something with the data, with the analysis, with the things that you're viewing to ask questions about your data, to see certain things in more detail, right? I've oftentimes used the analogy of it's like when TV first introduced TiVo, and you could rewind something because you missed it, or you could slow something down. This is right, the power of user interaction, and it's really fascinating as an area, and we're going to get into just a little bit of that, right? So a lot of what we've talked about is this, or amounts to this, right? Oh, we've used a nice color ramp here, and oh, we have a bar chart because we've used position because it works so well. And we've encoded things, I think this is like server load over time or something like that, and each color is a different service. And you can make out things like, oh, look, there's a peak there, and why was there a bunch of blue stuff happening earlier, and now there's a bunch of that yellow stuff happening. But in reality, our tools look a bit more like this, right? We have those things, but then we have a whole slew of control panels, of interface widgets, of other kinds of things around those visualizations, which are ultimately the handles and the affordances that we give people to be able to ask questions about the data. And this raises a whole cadre of other questions and challenges around visualization, because it's now no longer just the perception of seeing the information that's important if we want to foster usability or foster adoption or foster any kind of use or user experience of these systems. But now it's also the ways that users input their own domain expertise and knowledge into a system that lends itself to explore things like which kinds of menus work better, what kinds of interface widgets are more usable by certain types of users, what domain expertise lends itself to some kinds of controls but not others, and all those perhaps more HCI-oriented research questions that come out of that. Sort of an engineering approach to user interaction is nicely illustrated by the InfoVis pipeline here from Stu Card and others, back in I guess the late 90s, yeah, where we see that InfoVis, in the sense of what we've talked about so far, goes from transforming raw data using some sort of transformation into a data set or a database or whatever it may be, applying some sort of visual mapping to it that we discussed, getting it into visual form, right? Big step just to get to that. Then embedding it into a visual metaphor, such as the bar chart that I just showed, to get to the view. And then there is this function, if you will, to use perception and cognition to get it to the user. But then there are all sorts of things that happen in our head that we want to tell the system about, right? And that's really this entire bottom line here about the user interaction that can be on things like the transform, right? I want you to not use that data when you actually import it into my data set. Or I have other data sources that I want to use. The visual mapping, right? Oh, I don't want to use shape, I want to use color. Or the view transformation. I don't want to use a bar chart, I want to use a scatter plot, right? So there's all sorts of those things that a user can ultimately interact with. And I think this helps sort of illustrate the many stages along the process of just the InfoVis pipeline where that interaction can actually happen. To frame the discussion, the short presentation I'll put here about user interaction is largely pulled from this particular paper here, this study. And it's toward a deeper understanding of the role of interaction and information visualization by John Stasko and some of his students as well. It's a great paper. It's got a bunch of references. I know some of you that like these sort of survey type papers, this is a great one to look at. But the discussion that I'm going to give now really is in large part about this particular paper. Quick overview of how the paper worked. So they surveyed a bunch of papers, a bunch of InfoVis papers. They looked at the actual mechanism for user interaction. They also looked at commercial systems, right? The Tableaus, the TableLens, Spotfire, so on and so forth. And collected 311 individual interaction techniques, right? So what are the things, what are those handles, those knobs, those sliders, those buttons in these interfaces? Went through an infinity diagram method to try to group them and categorize them, and then presented these categories. And key, I think, to this is that they didn't focus so much on sort of the technical operations and how they work, right? When they saw a drop-down menu, they didn't say, oh, well, this evokes an event that lets the user select between one of n things in the array list or whatever you may want to do, but focus a bit, a bit more on what is being done by the actual person and what is that purpose, right? And so now we're going to walk through this 7 categories of the results that they have, and I'll show little demonstrations of each of them. And again, these are the low-level operations that people can do. We're going to build up to the higher-level things that people can do there a bit after this. So the first is select, right? This is probably one of the basic fundamental things you want to do in a visualization. You have a view of your data, and you want to be able to select one or more of the items, right? Mark something as interesting, see more details about something, pull up more information on it, things like that. We can do that by actually clicking. We can do that by hovering. Touch is a bit of an issue, but I think we're going to work that out eventually. Here's an example, right? This is the sort of TableLens view. Who here is familiar, has seen this particular visualization before? Yes, finally something new. Yeah, so what this is actually, I'll back up a bit and talk about this visualization. What this did was it basically said, starting with a spreadsheet, how do we put visualizations in each cell as opposed to the value that's in a typical spreadsheet that we see, right? And so we see longer bars or shorter bars here for the amount, the value that's in that actual cell to give people more of a overview visualization of a spreadsheet as opposed to just the standard spreadsheet kind of view. Not really all that relevant to the tooltip here we're describing, but it does say that one of the things that this then lacks is, well, what is the value underneath that bar, right? And so here we see it hovering over one of these actually gives us the detail of, this one is Fruit Loops. What is this, cereal, I suppose? Yes. The Fruit Loops particular row there, and we do that by selection, right? Bringing up information. More recently, 2008, I guess, Jeff Hare and others had this particular bit of work here, which I always found really inspiring. It was this idea that you have different levels or different, I guess, granularities of the selection that you make, right? And so if we start all the way over here, we can select, and it will select that one point, right? Kind of like what we just showed in the previous visualization. But then as a function of dwell time, how long we click or how long we hover, it actually relaxes that query, right? So if we move over one, we now see that it's no longer just that single item, but it's actually the entire column that it starts to select. If we dwell longer, it selects not just the column that's directly in line, but a bit out of that column. And then ultimately it also goes into other areas. I don't know if you dwell forever, if it selects everything. I actually don't know the details of that. But it's this idea that the length of the interaction might also have something to do with it, beyond just the I click and I want the point right under my cursor. Right? It may be that I want to go out a little bit from that selection. The second point is, explore. Right? The idea that people want to see something different, show me something different, right? And this is often realized in visualizations by things like panning and zooming, for example. I know we have probably all done panning on Google Maps, so I'm not going to show an example, but that would be one thing you would see here. And this used to, and probably still is, something to overcome the limitations of display size or resolution. But certainly other things as well. The third one here is reconfigure, right? I want to see a different arrangement of the data. Provide me a different perspective by changing the spatial arrangement or representation, changing columns in something like table ends, reordering things, changing the width of my subset in my histogram, for example. All these kinds of things ultimately allow me to reconfigure what I am seeing in the display. Right? Here's an example, again, using table ends, where I can drag one column into a different spatial arrangement in this data set in order to see some different pattern that might emerge when two columns are near each other, as opposed to all the way on the other parts of the display. Right? Where making that comparison between them is made more difficult by the actual space in between the two columns. Another one is sorting, right? We've seen the ability to sort columns, and then in doing that, you might be able to see correlations visually to others as a result of that. The fourth here is encode, right? And this is really about showing a different representation and changing that encoding, right? Those things we talked about, color, size, orientation. And it really changes the visual appearance, but also could change the amount of or the type of insight that you actually get out of it. And another one is this idea that you actually change the entire visual representation. So it's not only the mapping, but it's the representation altogether. So an example here is going from a scatter plot over here to a parallel coordinates view, where in the scatter plot, you have every point, every data item is actually a circle on the display. You can see we've mapped some attribute here. I believe it's miles per gallon maybe, to size of the point. So some are bigger, some are smaller. But in our parallel coordinates plot, every data item is actually a line drawn through each, from all the way from one side to the other, where each bar here is a feature of the data. So this is cars. Yeah, this is a cars data set. And so we have things like manufacturer, miles per gallon, cylinders, displacement, horsepower, things like that. And we can now see all of our variables drawn like this. And this is really changing the visual encoding, or actually the representation altogether, which is a frequently observed operation in data visualization.
Can I just ask, right?
Yeah, sure.
Okay, I think you did a break. That's why I thought at least.
Yeah.
But so from what you just said, I mean, there are fewer variables encoded in the scatter plot than the parallel coordinates.
Mm-hmm.
Clearly. So you selected 3 maybe, put them in the scatter plot.
That's right. And I think this is also, we're going to talk about parallel coordinates again later, but this is a great time to bring it up. It also changes the complexity of what you're seeing visually, right? Parallel coordinates, while they can show a lot of information, a lot of data attributes at the same time, without the interaction of being able to select a specific data item and observe, you can barely see it. The yellow line throughout the entire parallel coordinates plot, it's very difficult sometimes, often actually, to trace a single item through the entire parallel coordinates plot. And so I think this amplifies the idea of brushing, which is another kind of interaction that we'll talk about, or even just selection, when you go from something that is visually much more complex to something that encodes fewer features of your data, but but is visually much more simple. That's a great point. Other questions? Abstract and elaborate. So this is this idea of showing me more or less details, right? Zooming in, zooming out, doing things like semantic zooming, where it's not only making something bigger or smaller, but actually revealing more information about an area you're zooming into as opposed to zooming out of. Again, I like to use the Google Maps example. It doesn't just make the font of the thing you're zooming in bigger. It actually shows you more information about the details of the area you're zooming into, and things like that. And this brings us to one of the cornerstones, if you will, of data visualization, which is this idea of details on demand, right? And this is a term that's part of Ben Schneiderman's sort of mantra of data visualization, which is this idea of overview first, zoom and filter, details on demand, right? And it's really, it's nice to be able to wrap the interactions and the thought processes of people that we try to invoke into a mantra like that. And I don't think I could get away with a talk that says the overview of visual analytics without mentioning it, but I'm sure many of you have heard it before. And as my grand advisor, he probably would not be very happy with my educational upbringing if I didn't. But it can go either way, right? It can go from something that's a more detailed view into something that's more aggregated, which I think is equally interesting as the showing me more details on demand is this idea of aggregating on demand, right? Sort of going in the other direction. Filtering. This is this idea of conditionally showing me something. So I have all my data, but I only want to see some subset of it. And I'd like to tell the system what that subset consists of. What is it limited on? What are the filter criteria? What are the ranges that I want to be able to subset my data of or from? It's also, well, I guess, yeah, it's another one of Ben Schneiderman's early work on dynamic querying, right? And this is a well-known and early example of how we do this conditional selection or conditional showing of data attributes in a visualization, right? So what is this thing? It's I guess there are these constituents or design guidelines of dynamic queries shown by some of his early work in the mid-90s there that says it should be rapid and incremental and reversible actions, right? So I should be able to do something to tell my system something, select something, and see it change rapidly in the visualization. And this was, to get sort of a little bit old school here, right? The point here was you should be able to select it graphically instead of typing, right? That's at the stage that we were often at with this type of stuff. And it should be immediate and continuous for all results. And now I'm going to show a really old school image. And I love this image, even though it's hilarious to look at. This was the prototype they developed, right? It was called Home Finder. And if you squint and use a bit of imagination, this is actually a map. That blue thing is a river. The black is land. And this was a prototype that showed this particular bit of interaction, right? So you have filters and sliders over here, which allow you to say, I have point A on my map, and I only want to be so and so many miles or kilometers away from my point, and I want to remove all the other data. I have a number of bedrooms I would like in this house, right? And so I can do a range selection, right? I can actually select from two ends. I can say no fewer than 2 and no more than 4, right? And this was really powerful way to get people to, for one of the first times, to be able to say graphically and visually the kinds of things they want to conditionally filter on, right? And I don't know how many of you have recently used sites to look for apartments or houses, but things like Zillow and Redfin. It's remarkable how 20 some odd years later, the interface, granted, is now on the web and looks a lot nicer, but the interactive widgets that go into that still resemble this a great deal. And I think that really is a testament to the fundamental and theoretical work that went into putting this bit of research together. Right, and so, whoops, I guess I should have actually put this on the other slide, right? And so the types of things we control are variables that are binary, right? So we have buttons. So I'm going to do a little bit of flickering back and forth, sorry. Right, the buttons that let you look at things like different features or different areas here, right, like the reset and quit and things like that. You have things like the nominal values that have very low cardinality, those radio buttons that we had, and then the quantitative sliders, right, like the number of bedrooms and things like that, that are in that data set that allow us to do that, right? And this is one way that we can get around sort of the complexity of data, which I think many people would say that that particular bit of data that was shown there is not complex in current age, but interaction is still a nice way to get around that. Embedded in that was this idea of the range slider, right? And this is a particular kind of slider where we actually encode a bit of the data characteristics into the interactive graphical widget, right? So we don't just give users a slider that says, please go from 0 to 100, let's just say bedrooms. There's a ton of data off into the blue or dark gray space where there is no data to support that particular range that you might want, right? And so this is the way that we start to give people a bit more information sent about the actual valid areas that they can conditionally filter their data, right? And we give them these two, high and low thumb sliders to do that, and then this white space in the middle is actually showing you data exists in this region. And so this, if we think back to aggregation, when we talk about lots of data, is one way that we can aggregate data to get people to see where the information exists, conditional on that one variable that that this particular slider is put onto. Here's an example of Spotfire, which actually uses this, right? So we have the dark yellow. It's kind of hard to see. Sorry for that. Dark yellow and light yellow, which shows areas where data exists and areas where data doesn't. We see the range slider used directly on the axis, which I think is kind of a neat place to put it, right? So there's a bit more proximity to what you're conditionally filtering on than to just put it over here into the toolbar. Right, so we start to see a bit of those Gestalt principles and other things actually come into play here as we design this interface. And again, this has been revamped many times. This looks like Windows something that probably still had a real number to it. But regardless, we see these principles make their way into interfaces. We can go a bit more sophisticated, right? Which is showing more of a bit more of the data in the actual interaction, in the place where users interact, where you actually show the distribution of the data. It's not just a binary, data exists or does not exist, but it's a bit more granular, right? How much data exists in these different slices, if you will, of my conditionally filtered data, right? This was particularly nice because you can do other things here as well, like change the algorithm that you use to calculate the distribution, right? You could do things like showing the variance, showing other things about your data actually in that range slider. And that's a really close connection to where the user can start to think about areas of the data that are more or less interesting to explore and the characteristics of the data as algorithmically computed, right? So here, this is a simple distribution, but you can start to think about mapping more complicated things onto that particular visual technique. Here's a fun one. This is also coming from John Stasko's group in 2005. Dust and Magnet. Who here has seen this? Nice. Few of you. Good. So this particular visualization is another example of putting controls, the user interaction, directly in the visualization, right? So while there are some things over here that you can filter, one of the primary user interaction contributions of this work is what goes on in the visualization. And what you see here is you again have serial. Serial and cars seem to be like the two data sets oftentimes used, right? So we should have no problem making a best decision about like cars to buy and cereals to eat, because we have plenty of visualizations for them. Anyway, sorry. The two things you see here is one is the squares that have things labeled on them, which are your attributes of your data, right? So your sugars, your sodium are the two things in there right now. And then your colored circles are your cereals. And what this particular tool lets you do is to treat each attribute as a magnet and each data point as a, what did you call it, like a piece of metal dust or something. And then you can pull these magnets around and see which items get pulled towards the magnets based on the amount of, or the amount of that feature that they exhibit. So the very sugary stuff is going to go up near the sugar, and the very salty stuff is going to go down to sodium. And then actually there's something about the amount that you wiggle the magnet, the more of that dust is going to come down there. And it's a really interesting example of really putting, well, one, mapping, using the spatial or positional visual feature in an interface that actually allows you to directly interact and manipulate that. Right. I tried to get a version of this, but I don't think there's a way for me to run that anymore. But it's really fun to play with. Yes, Russ? I think that in this particular screenshot, somebody has zoomed in and cut off what is probably a magnet somewhere over in this region. But yeah, that's a great point. I assume there's a magnet over there. And I don't know if there's a way to tell which one it is, but that's why I use sugar and sodium as the example. Other questions about this particular view? Yes?
Broad question.
Sure.
To what extent does this apply to data and motion as opposed to stats? Carry across? I mean, a really simple example might be an old-fashioned oscilloscope with compute time base and amplitude and stuff. That's kind of like zooming in and out, abstracting.
That's a great point.
Because a lot of data now is flowing constantly alongside.
Right. Okay. Yes. I guess let me split your question a little bit. Animation in visualization is something that is used very tactfully and sparsely, I would say. A lot of the visuals of data that we create are often not as animated as you might see when you say data in motion. Now, the second part of that is the streaming data concept, real-time monitoring, right? And I would say the visual updating as new data comes in. And I would say that is a newer area for visualization to get into. Yet a lot of these foundational components still apply, right? We still need to look at things like change blindness and how different visual features actually impact that less or more, right? So this idea that as I flash new things in front of you, the rate at which I flash those, the faster it gets, the more unaware I am of the thing that changes, right? And certain visual features, like the color, the position, and so on, have different impact to that particular thing. So that's an example of how that very basic primitive thing actually makes its way all the way over into your Bloomberg terminal, right? Or other things that do streaming information like that. There are a whole slew of other technical challenges around how we update our analytic models with new data coming in, what we show to people. Do we show people only the thing that changed, only the stuff that stayed the same, the stuff that changed in context of the stuff that was there before? How do we get stuff out of the view as new stuff comes in, right? Because at some point your screen is going to be full, then what do you do? And so I think it raises many new questions, but I do think a good amount of at least this fundamental stuff that I'm covering in this first half still apply to that today. That's a good question. 10 minutes left. Okay, that's good. I think I'm okay. Hard to tell. Here's another example. This is actually here. Why don't I talk about it before the video starts playing? This was my dissertation work actually at Virginia Tech, and it's another example of putting the control of the visualization directly into the visualization. So the use case here, if you will, is intelligence analysis of text. So here we have every dot is a text document. This particular one is probably one of the VASS challenge data sets back from the earlier ones where there's this fictitious hidden bad activity that might be happening, and your job to solve this challenge is to read through these documents and come up with a course of action to report to some manager. And this led to a whole slew of interesting concepts. One of them was this one here, where we said, well, how can we use dimension reduction techniques and put the controls for those dimension reduction techniques directly in the visualization. And the details of that is actually in the second half of the talk in some later slides. But for now, the key point I wanted to get across here, and I guess I can let the video play while this happens, is we want people to directly be able to form clusters and observe how similar documents, based on entity extraction and topic modeling, things like that, actually come over near the clusters I'm forming. So over here, it looks like I'm forming a cluster around, I don't know what that word is, Russia or something. And up there, I think I have like Texas or Atlanta or who knows what that thing is. But the idea is as I start to pull things closer together, the system learns from my user interaction and actually updates the spatial clustered layout as a result of that, right? And we're going to walk through the details of how it does this a bit later, but you can see sort of the extension onto that dust and magnet work where I've said, well, instead of dust and magnets, how do I have just my data? And what can I do with just my data that still allows me that really nice interactive control over the visual display that I'm seeing, where now I see, all my stuff over here that has to do with Russia and some of the other keywords are down there, and the stuff that are the clusters of keywords that have to do with, I can't read that, are over there. And the details we'll talk about a bit later. There's some fancy math and other things, and we'll chat about that in the computational part of this talk. The seventh point here, and the final one, is show me related items, right? The ability to connect based on the relational or the relationship component of data, especially when you have more than one view, right? And this idea of brushing is actually central to this, right? It's to say if you have more than one view, how can I do a selection in one view and see it propagate over into another view? Because like we saw earlier, a single view like the scatter plot versus the parallel coordinates that we saw can only show some subset of the features or data characteristics that our data ultimately has. So having multiple views is a nice way to actually select an item in one and see how that selection propagates across others. Right, and here's a very basic example of that. I've got this scatter plot on one and the scatter plot on another. I have two views. I do a selection in one, and that same item is highlighted in the adjacent view to allow me to perhaps see how different features on the X and Y axis here align with my selection that might mark my item of interest in the other view. Right. Yeah, I can probably squeeze this in before the break. Tasks, right? What do people do with visualizations, right? And at a high level, there are two primary things. One is analysis and one is presentation. And I think analysis is perhaps the more attractive one, right? Or especially the one that's been talked about and researched a bit more. This idea of I have data, let me have some visual interface to control it. But the presentation one is actually also an important one. I know it was talked about in the keynote where it's, I've now done all this work, I want to show it to you. How do I do that? Right? Do I hit print and show you my final visualization and expect you to understand all of this magnificent insight that I got out of what's ultimately an XY scatter plot where I put two things on there and I said, but that's the answer, right? And I think there's a whole lot to be said in the way of analytic provenance, which I know is a talk later sometime this week, about how I now package all of that stuff that I've done in the analysis into the presentation of my results. And I'm really looking forward to that talk later this week. And I think, right, sort of talked about that. Analysis, given all the data, let me decide, let me judge, let me evaluate, things like that. Really that active analysis of the information. And ultimately it's about solving problems and gaining insights. I want to just quickly remark on this. As much as an advocate as I am for data visualization, I think correlation and some good statistics and data mining can go a long way in very specific examples, right? I would not advocate for always using visualization. I can rattle on about examples of why you would and when you would, but I think it's also good to acknowledge places where not to use a visualization. And this idea of if you have very specific and clean data and very specific and clean questions and tasks and approaches for them, it may just be best to run that analysis, to automate that, to offload that. Right? For example, I don't want to have to do a visual analysis of my wireless router to figure out everywhere that every packet should go in my home network if I'm not interested in things like security or things like that, right? I like the fact there's an algorithm on my router that tells every packet where to go. Another example here is if my explicit task is to figure out what the average temperature is yesterday in this particular well-defined region, I can probably run that in an automated kind of way. But Viz is good for generating questions. I have a slide for this. For generating questions that you didn't know ahead of time. And I think that's actually a very powerful and often understated part of data visualization, is this idea that you may have your data and some set of questions, and that's how you start your analysis, but through the course of your visual data analysis, you come up with additional questions that you didn't know you had about your data until you saw it, until you saw these visual features, until you saw a cluster that doesn't make sense to you, until you saw an outlier or a spike in your data, and you said, why is that there? And I think that's actually a really sort of counter-argument to this why not to use visualization, or when not to use visualization that I said before. Right? Really echoing this bottom part here. When it forces us to see what we were not expecting. Right? And it's often happened with visualizations that I've seen. Where am I on time?
3 minutes left.
Okay, sounds good. Right? Examples of things for exploratory data analysis, right? Things like, why has Apple sold so many iPhones? Or how much does a marketing campaign have to do with that? Right? These are very sort of business examples of, I have this large question about a particular area for which there is certainly data to support it. I now need to just start exploring it and getting a feel for the data, understanding this space, this phenomena of Apple and selling phones a bit more, and visualization is a great way to do that. Back to this example, right? House hunting, finding which house to purchase, I think is a really great thing for visualization. I wish there was more of it. Trust me, I just went through this process. And right, why do I like certain homes? Right, what is it about the area? Do I know the topology and I want to live at the top of the hill, not the bottom, or I want to live sort of right along that bend of the river, but on the inside, not the outside, because the outside floods very often, right? I really have to do these trade-offs to help me understand sort of what it is I'm ultimately wanting. At some random time of thinking of this, I had this interesting thought of, well, if Google, with all the data that it may or may not have about me, could have a data mining algorithm to tell me exactly which house to buy, right? And then I have Apple Pay to just pay it. Would I ever trust an algorithm that just says, here's my bank account number, purchase my house? You know which job I have because my contract is in the email. You know my start date because that's in there too. You know all that stuff, right? So you could probably do some optimization function over the house to buy, but would you trust that? And would you use it? Or would you like some user control, some user in the loop to be able to guide certain things one way or another, some idea of the context of how that answer came about, some visual representation of choices and trade-offs that are between one house and another, things like that. And I think we'll talk about a bit of this, not this particular example, but a bit of this idea of giving people the ability to weigh computationally their preferences and express those, to guide the computation, to suggest visualizations and items that are more of interest to the user, and ultimately foster more interpretability and more trust in the actual visualization. And I have the stop in front of me, and I think that's a great place. So now, after some coffee, we're going to talk about sort of putting all these little fundamental bits that we just talked about together. And I see that most of us have made it back, so I think the attrition rate is pretty good, which is good to see. We talked about this as sort of the InfoVis pipeline earlier, but this is sort of a minimalist view of the visual analytics pipeline, which really is a great starting point for the second half of the talk. And one of the key blocks, if you will, that is new in this diagram is this looming thing here called the algorithm, right? Or the computation, or the mathematical model or the analytics, right? That's part of visual analytics that we stick in there, which is then this additional thing that the user has to interact with and changes a lot of the challenges within the interaction principles that we outline, right? On the other hand, beyond the challenges, there's the opportunities of the synergy between the strength of human and computational data processing, right? The perceptual things that we talked about in the beginning about perceiving information are really coupled with being able to offload some tasks to the more computationally, some of those computationally attractive tasks to computation, right? And this diagram here, again, is from Daniel Kime, where he sort of says the best of both sides, right, is somewhere near the middle there, merging this thing of the human and the machine. Right, so this idea of integrating data mining and machine learning into visualization can come through in a variety of ways. And I think each of these I will touch on with some demonstrations, right? And there are certainly others, right? It's not limited to these. The first and possibly one of the more commonly used one is dimension reduction, right? This idea that we have data that may have more dimensions than even that serial data set, but we only have so many visual channels and so many pixels on the display. So how do we reduce the dimensionality mathematically to something that we can then show to the user, right? And we use things like PCA, MDS, several others. I'll walk through some examples of that without just throwing acronyms your way. We can do things like feature selection, where we actually extract certain entities if we're talking text, certain phrases if we're talking text, things like that. Similarity functions, right, where we actually define distance metrics between data points to say, if I think these two documents are similar, can you give me an objective distance function that defines that similarity and use that in some way in your system. Things like prediction, right? Given time now, will this stock go up or down, right? One of the canonical examples, perhaps, of doing prediction analytics. And again, certainly others, but this is just some of the concepts that we'll talk about. So for dimensionality reduction, I think first we should talk some data, and specifically what we mean by dimensionality, which is oftentimes also known as features of the data, attributes of the data, variables of the data, right? We're really bad with this because we've got a lot of words for the same thing a lot of times, and it makes it confusing. So please excuse if I flip between those throughout, but know that what we're talking about is really the variables even, there's another one, that we use to describe a data item. So the potassium and sodium of a cereal, the miles per gallon of a car, right? Things like that. And as we start to increase the cardinality of the dimensionality of a data set, it often leads to what we call this increase in complexity, right? Because it gives you more and more ways to describe a data point, like a car or a brand of cereal. We've talked about this, right? Data is taken from something that happens in the world. It's often sensed or collected or created. I think it's important to note that the difference between what data is versus what data approximates, right? Oftentimes, we like to think that the phenomena is what the data tells us as opposed to approximates what the data tells us. Right, created, sensed, produced, all those things, right? This, I think, is a schema of the car data set, which we'll see quite a bit of the examples here use. Right, we have cars. They have things like the make, the model, the year it was produced, the fuel efficiency, cost, number of cylinders, how much it weighs, right? Things like that. And these data models that we have, or schemas, really consist of the items, right? Like a student, a car, attributes, and relations or relationships between two data points, right? How do they connect? Things like that. And actually, I think we're gonna the relational one is actually not covered as much today. There's a whole slew of approaches once you start having that, because you can model it in the way of graphs, and then you get into graph analytics and graph visualization. I don't have so much of that to show here today, but I do want to acknowledge there's a significant amount of work in that space, partially perhaps because a lot of the data that we have now models a larger ecosystem of data which is connected and does resemble the form of a graph. Right, so if you think, if you map that schema then onto tables, what we oftentimes get is something like this, right? Where you have cases and variables and then values for those like you would in an Excel spreadsheet, right? If you actually fill this in, what you have is you have some ID for Mary is 145, you have an age, you have hair color, you have GPA, so on and so forth, right? Pretty simple, and ultimately it leads us to representations, which are visualizations that look like this, right? Pretty basic, but worth noting sort of how we built up this idea of spreadsheets as a representation of data, and also what we do with them now that we have this very malleable, workable representation of information stored in some way. Real quick, it's worth talking about types of attributes, because this is actually important when we start thinking about how we visualize them, right? We can have things like nominal attributes, where it's like an equal or not equal relationship, right? Things like gender is one example there. We can have ordinal, right? So ordinal data actually obeys some sort of a less than, greater than relationship. You can think of it like an ordered set to some extent, right? If you're familiar with the Starbucks naming scheme, right? The Grande coffee is smaller than the Venti one. Small T-shirt size, medium, large, right? There's something that can be done to be said is large bigger than small, right? That you could not do with is male bigger than female, right? And then ultimately, sort of the final stage of this is quantitative, right? Type of data, and these are the ones you can do math on, right? Age, weight, and a lot of our data resembles this type, and it allows us to do lots of things with analytics that allow us to do that. Each of these types, there's also, of these dimensions, there's also how many dimensions you have, right? Data sets are oftentimes, 1, 2, or 3 dimensions, right? They can be univariate, bivariate, or trivariate, and we can simply visualize that information and get quite a long ways with it, right? If you have items, maybe courses, and number of students enrolled in those courses as your one variable, a bar chart is a pretty good way to show that information, right? Because you have one variable and one item, and a bar chart is great at showing that. Bivariate, perhaps a scatter plot, right? We talked about mapping something onto the x-axis, another attribute onto the y-axis, and if all you have is 2 variables, that's a great way to show the data. But as you start to move down and increase this dimensionality, we start to look for more sophisticated visualization techniques, but also help from computation, machine learning, things like that. And that's why I said we will revisit this, my little note to myself there, when we talk about dimensionality reduction, especially for hypervariate data, right? And I oftentimes say that I think this term may be aging off a bit, right, in terms of hypervariate data, because now I like to think of this as maybe big data or complex data or maybe just data, right? Because I think more and more we're starting to see the data sets we have being described by many attributes, if not fused with other data sets, which then appends onto this long list of attributes that you then have to describe an item or an object of your data set, right? So, what do we do? Actually, I want to... I'm going to skip over this. I thought I took these out. Tables and graphs, we've talked about. Graphs is not something I'll talk about much. But back to the question of what we will do. Well, one of the things we can do is give each variable its own display, right? So here we have a data table, right? We have item 1, 2, 3, 4, 5 over as rows, and we have each column as a variable, A, B, C, D, E, and we can say, well, I'll just make a bar chart out of each one of them individually, right? Because I don't want to put 5 variables into one, right? A scatter plot where color means one thing, shape means one thing, size means another thing, and it creates this big mess. I'll just spread it all out, right? I'll decompose the problem. And this creates views like this, which oftentimes are shown in what we call a scatter plot matrix, where you actually have, again here, wow, that looks horrible, apologies for that, where you have all of the attributes of the car data set sort of visualized in this matrix pairwise with each other. And now the user's got this overview of the data, and perhaps he or she might find one of these that's particularly interesting, click on them, zoom in on them, show the details of that one. But this is sort of the realization of this idea of how do we decompose the feature space of a data set into these small multiples that give you this overview of the data, right? Another one, we showed this one earlier, is parallel coordinates, right? Who remembers some of the issues with parallel coordinates? That's cheating. I know you do. What's hard to see? Yes?
It's hard to see a single entry.
That's right. Right? So the advantage was you can actually see all of the items as a line. Each item is a line here. And you see miles per gallon, cylinders, horsepower, weight, year, and you see the data across all of these variables, right? And we haven't even used other things like color or things like that. However, it's difficult to see a single item without things like selection to trace it through the entire space, especially when it starts to get into a bit of a mess like it does over here, right? So that's one of the drawbacks. Great. Yes. Overplotting, hard to trace a single line. What other techniques exist, right? This is a fun one, right? Who here has seen this? Oh, a few of you. Great. So this is an interesting approach for showing hypervariate data, where you can create the icon of a face, and you have these visual attributes, right? So not like color, size, shape, whatever, but actually things like mouth width, mouth openness, nose width, pupil size, right? And you can map your data dimensions onto one of those visual attributes, and now an item of your data generates probably a unique face that has really weird attributes, right? Like a really tall, skinny one with really big eyes and a small mouth, right? And that might mean something as just a fun demonstration of mapping hypervariate data to a visual depiction, right? Kind of fun. There's some interesting examples of this. Or let's use some computational horsepower, right? Our CPU's been sitting here not doing a whole lot. We've been making funny faces, but why don't we sit here and crunch some numbers as a way to get us to help reduce this dimensionality down to something we can manage. And dimension reduction is a computational technique that allows us to solve for attributes or dimensions that are similar and can be merged, right? In a really basic demonstration. And it's worth pointing out that this is a lossy transformation, right? You are losing some bit of expressiveness of your data when you do this, but you're sacrificing that for the ability to reduce your dimensionality and give users a more simple visualization. And this is actually a theme that cuts across more than just dimensionality reduction, but also to things like aggregation, right? As soon as you aggregate data, it is lossy, but you're doing it because you want to ultimately show the user something that's more simple. Right? So, for example, in visual analytics, what we often do is we take high-dimensional data, right, 20, 30, 80, 2,000 dimensions, and what we don't want to do is show somebody an 18-dimensional scatter plot. We probably don't even want to show them a 3-dimensional scatter plot. But 2 dimensions actually works fairly well, right? We don't have things like problems with occlusion like we do with 3 dimensions. We don't have things like the interaction of how you zoom around in the space and all that. But 2 dimensions, we've shown, works fairly well. So often, we go from n dimensions all the way down to 2, right? So you think about the compression that happens there. It's actually quite phenomenal. And we'll talk about some techniques that let you do that. I'm not going to go through the math of PCA, or Principal Component Analysis. Who here knows about this? Wow, awesome, great. Very good. Ultimately, it is a deterministic technique for solving for principal components of your data set that you can then map to axes of your scatter plot to do that, right? And so what you basically do is you map those axes, those principal components to axes, the x or the y, and the y. And then you generate a scatter plot, which shows you some reduced dimensional space of your high or hypervariate data. I do want to point out some limitations of PCA directly, just so you don't think it's like the one to use all the time. You're going to go run and always use it. It's a good one to start. However, as with other computation as well, there's no guarantee that the top two principal components that it finds that you might map to the x and y axis of a scatter plot are the most meaningful or most important in your data. And I chose those words specifically because meaningful or important are very human-centered metrics. And PCA is purely looking at the data characteristics that is in your data set. Right? It does not have a important knob that I can just increase and say, more important, come on, go. Right? It solves based on your characteristics of your data. It's also very sensitive to outliers, which is why oftentimes perhaps that first or even second principal component in the long ranked list of principal components that it returns may not be your optimal one, given that you're going for insight or meaningful views or so on. Also, to get not too technical, it's a linear function. So if your phenomena or that's in your data that you're trying to model is nonlinear, there are perhaps other ones that are more along the lines of manifold learning that are actually the ones that you may want to consider. Any questions about PCA? That was super quick, but I saw a lot of hands go up about PCA, so I won't spend more time on it. Okay. K-means clustering, another really basic one. Raise your hand if you've seen it. All right. So then I will quickly walk through this. Starting with A, the way that it works, I like this instead of showing the math because it's actually visual. Imagine that. The way that it works is you can randomly assign or smartly assign two starting points there, the red and the blue, and then you find the space around it. You take the average of that and you move that centroid, and you do that iteratively over and over and over until you find some stable set, and that is how K-means finds clusters in your data set. Right? You move the centroids until there's some stability. Animation is a great way to show how that actually works. And the goal here is to partition your data set into K clusters where you can then do something with those clusters, right? You can show them, maybe these are the ways that you aggregate the data, right? And you show that to the user. Potential drawbacks, trade-offs, is you have to define K, right? There's some methods that get around that, but you have to start off with doing that. And it also uses a Euclidean distance for the actual computation, which could be error-prone given what your data is actually showing. All right, so I'm actually really happy to see that a lot of hands went up about PCA and K-means because they're really great fundamental places to start when you start thinking about how to integrate these two into visualization. If there's no other questions, actually, are there any questions? Because I'll just walk through an example about text analysis particular after that. Okay, great. Okay, let's do an example. We'll get to some demos and other interactive stuff after that. So text data is actually a great example of hypervariate data, or it can be if you go through this kind of a process here, where you start off with documents. Documents are a bag or a collection of words, right? We can then look at how those words, we can say each word is now a dimension of your data, right? Each unique word. And that creates this massive spreadsheet or matrix, right? Lots of dimensions of your data. And then we can do things with that, like look for dimensions that we can start to collapse, right? Maybe similar words that we don't need, and actually do that dimensionality reduction to ultimately get to 2 or 3D displays of the information, right? Here's another way to look at that. Right? You have your unstructured text at the top, just think raw .txt files. You go through entity extraction or feature selection to pick words that you want to pull out of that data, out of that document. You map all of that into what would then be considered structured or semi-structured text, where you have it in a spreadsheet form. you then do you then have this sort of high-dimensional co-occurrence matrix about which terms appear in which documents and things like that. You then go through the dimension reduction models, like perhaps PCA that we just talked about, and ultimately, when you map it to a visual metaphor and the encodings and things like that, if you choose to do it in a scatter plot-like approach, you come up with a view that might look a lot like this, where you have clusters of terms, clusters of documents, right? Each document is one of these very, very faint gray dots that have this blue glow around it. And each one of those clusters is actually similar based on a set of those principal components of your original higher dimensional data, right? And so now the person that looks at this doesn't have to look at this massive high dimensional matrix of your data, but can look at it in a very lossy but useful encoding that we've created, where clusters start to reveal topics of interest or topics of similarity amongst documents. We could give them little labels, like this particular tool here has. Is my next slide about? No, but I'll talk about that. And so on and so forth. There's a tool that I'll look into, or that I'll show, that actually does text analysis for pretty big document collections that we will look at. But this is one of the ways that you do text. Yes?
In this pipeline, do you think the clustering should be mentioned after the dimension reduction? Because
you could do that, right? Or you can simply, or what you can actually do is go directly from the output of a dimension reduction technique to the visualization, right?
then how would you interpret cluster from the dimension?
Yes. So, yes, what that would give you is maybe a space like this where the labels are not there, right? So what you might do is, if you do dimension reduction straight to the choice of the visual encoding, or straight to the viz, you will still have the dots in their spatial location, but you would need to leverage something like perception to see, there seems to be a group over here.
So you are supposed to do the clustering with the help of your visual choice. Because dimension reduction would give you just the a reduced set of attributes. So in order to make cluster, you should either use some algorithm or do some visual interpretation.
Yes. So in this case, or in the case of PCA, for example, right, you would get an XY location for every data point, and you would plot that XY location. And as a result, you would see dots. There's a pile here and a pile there. However, what you might do after that is say, I want a K of 2, and do K-means. And then K-means would say, cluster 1 is here, cluster 2 is there. And then you could do something like, what words appear a lot in this cluster and not in the other one? And that might be where you start to get some of these labels for these kinds of clusters, right? So we can start to layer these algorithms on top of each other. But that's a good point. There's certainly a lot. There's actually a lot that can be done. My next slide. In the entity selection stage, right? So you probably don't want to use every word, right? That comes out of a document, because there are certainly words that are more interesting or important than others. And this is a way you can start to prune that feature, that dimensionality of your data before you even get to.
So this is giving you an input to your dimension reduction model, this TF.
Yes, and it also helps shape the matrix that you get coming out. And oftentimes it's a matrix that has less dimensions to start with, because I guess what TF-IDF does is it actually allows you to compute the importance, the relative importance of a term given your document corpus. It stands for term frequency inverse document frequency. I guess, yeah. And so what you could say is, you could say, well, after doing this on my entire data set, right, and just to walk you through it real quick, you've got it up there, you can read. But it's a formula that ultimately spits out a weighting of each term. And then you could threshold that. And you could say, I don't even want to feed the words that are below some threshold into my dimension reduction, because I'm going to call those noise. Right? So this is one place where you can start to filter your data before you even go to the dimension reduction phase. That's a good question.
So just to
Yeah.
just to be clear on how that's done. So the
words which are less important, they tend to be the ones which are more frequent. Is that right?
Yes, if you run through the math, there's a bit of that. There's also a tail of a word that only appears one time.
Right. It also depends upon the corpus size itself. Like you just cannot say that the words that are appearing frequently are the important or the less important.
Yes.
It depends upon the corpus size.
Yes.
That's why you have put the inverse document frequency there.
That's correct. That's correct. And this is, I actually don't know the chronology of this, but this is one of the frequently used but often improved upon metrics for how you select words. You know.
Typically doing this inverse document frequency that actually helps to solve this problem.
Yes, yes. And you know, there are other approaches to doing this kind of thing. But you know, this is one way to think about your data in terms of its raw form, documents with words in it, and thinking about, well, if my ultimate goal is to go through this entire dimensionality reduction phase, how do I select which attributes to pass into my PCA before I just pass in every word in the English dictionary as a feature, right? Because I may not need it. My document, my data set of 100,000 documents, this word only appears one time in that whole data set. Or it appears in every single document, right? And so you can start to weigh the words and filter them in some way. And this starts to have some of those drop off automatically, if you choose to ignore them. Very, very good question, yes. And so the context of the tool, and I just heard this may be one of the things that gets mentioned in a demo or whatever else at some other time, so I'm just going to show the screenshot here, is Inspire. This was developed over many, many years at Pacific Northwest National Labs. It is a text analysis visual analytic tool. It allows you to import on the order of, I don't know, there are people that can give you better details of that are here from Pacific Northwest National Labs, but probably 500,000 documents is fine. Correct me if I'm wrong, I don't know. That sounds good. And basically, it walks through some permutation of that pipeline that I just talked about of saying, if I have standard text files or other ways of documents and just a folder of them, how do I get to visual representations of that data so I don't have to read every single one of them, right? And you can see that on top of the view that we have up there, which was the view that we generated by doing the high dimensional data, the co-occurrence matrix, and then finally the dimension reduction, we also have other views that we can leverage, given now that we have this structured, featurized data matrix of our data beyond just the text files that we had starting out. Right. And there's a whole bunch of views in this system. I would say it's probably the most full-featured visual analytics for text system out there. If you're interested in this, please talk to the PNNL folks, Chris, Russ, Dustin, that are here. It's actually a lot of fun to play with. One of the things it has is like the Google search. You can search for something on Google and it imports the data, and you can look at it in there. It's kind of fun. I like it. Oh, and your inbox. That's a fun one. You can shove your inbox into this thing and see that you have a whole cluster of, whatever, emails you didn't read. So, yeah, it's great. It's a lot of fun. But you'll notice that the thing that starts to come into play here as well is some of these control panels that you have, right? So we talked about the range sliders and all that stuff in the InfoVis stuff like an hour ago. But we start to see a bit of that come back because now we have this whole pipeline, right? The TF-IDF stuff, the co-occurrence matrix, all these other things. And now we have control widgets that we can give people at every part of these stages, right? And this raises a lot of interesting challenges, right? About incorporating user feedback, right? And the challenge really starts in the sense that the completely unsupervised automated computation is rarely the final solution, right? The view that comes out of all that stuff we did to the text to finally get to the 2D scatter plot is probably not the final view or the only view you will look at in order to understand your data, right? And so we're back at this, how do we transform the user from a viewer to an active participant in the data analysis process. And a lot of these ways of thinking about this are called this human in the loop design, which advocates for including the user in this whole holistic system. And it's really about this idea that people have a lot of domain expertise, right? They might know about words that are really, really important to them, where I don't care what TF-IDF says, that word needs to be in my feature space. Or they may know stop words that are junk and they don't care about. Remove it. I don't care what the computation says. And so there are trade-offs and there are balances of this subjective feedback that users can give. This diagram down here is one of this way of thinking about or integrating a bit of this model, this analytic model, right, like a PCA, for example, that we just talked about, or topic models, with a visualization into the broader activities that a human does, right? The tasks, like these things that we talked about at the low level, the stuff I didn't talk about, which was more of the sense-making, cognitive reasoning at a higher level, which I believe William might talk about later in the week. But all the stuff that goes on with the reasoning that we do and how we integrate that into, or I think they've even looked at this cloud of stuff over here on the computational side. Here's the the diagram like in the opening talk. Right, this is, I like sort of the articulation of it here from Daniel Keim and others, which is, at every one of these stages, as we, you can really think of it like a state transition diagram, where we go from data to visualization, or data to model, to knowledge, right? We have these parameters that a user can refine and augment in some way in order to generate a different visualization, or generate a different model of your data, a different, co-occurrence matrix, or whatever it may be, a different weighting matrix, parameters that we can refine, right? There are things you can tell PCA or k-means, oh, don't be, what's the distance you want to look for? What's the granularity you want to look for? All those kinds of things. And this feedback loop that we have, ties back into many, if not all of these stages of this model. And some of the examples that we're going to look at now, I think, really reflect well in this high-level view of looking at where and how do we plug the user into what we now have as a rather complex process, right? We're not just talking about the pre-attentive features anymore. We're not talking about, oh, do we use color, do we use shape? We're not talking about, do we use a bar chart or a scatter plot? We now have a whole plethora of analytic models to pick from. We've got a bunch of visualizations to pick from. We've got parameters about the data, about the model, about the visualization that we want to control, right? This is now very quickly, over the course of the last hour, turned into a really complex system that now has a whole bunch of stuff to control, yet we want the user feedback to be able to be active in the system. And this raises really interesting challenges, which the next few slides here will illustrate as well. Any questions about this at this point? All right, exciting stuff. Good. Here's an example. We talked about PCA, so this is a nice place to start. This is a tool called iPCA, developed with by Remco Chang as well as others in 2009. And you can see up there, this is what I talked about. This is what happens when the result of PCA, you simply plot the points in X and Y. You get their X and Y position, but there's no clustering, there's no labeling around it. I believe the color is some ground truth data set that they used in this case to show it. But I really want to draw your attention to the control panels that are now included in this particular example here. So what we have at the bottom, labeled E in this one, is actually the importance from 0 to 100% of each of the individual dimensions of your data set that this particular visualization is visualizing. I think this one is some bio data set, I forget. But the point is, users can now say each dimension, how important is this one? And as you move these sliders around, you will see the actual visualization change up there in A, right? Over here, you see this PC1, PC2, PC3, right? Those are your principal components. You actually select them, right? Any two of them to map onto your X and Y axis, right? Because we talked about sometimes your first principal component is not your most meaningful one. Should I pick a different one, and how does that impact things? Right? And actually, well, I'll skip the YouTube video, but there is a YouTube video about this. It's a nice system to see, but I do want to highlight how we have now changed what these types of controls are controlling, right? Yes, this is still a slider, just like in the home finder example, right? Those are still buttons or checkboxes, like in that example, but it's no longer that the interaction is about filtering values in your data. You are actually now controlling aspects of your analytic model, right? And that's a pretty significant shift when we start to delineate the stuff that we talked about earlier to the things that we're thinking about now, both in terms of technically, right? What does it mean to choose these weights, but also what does it mean to expect a user to know how to manipulate these things, right? And it's much different to say, I expect a user to know how many bedrooms they're looking for in a house, to I expect them to know whether to choose the first or third principal component, right? So that is one of the things I really want to highlight out of where we're going with this work. So, kind of the tagline is this idea of, well, how do we couple these two things, right? Our cognitive mental models, our data models, right? We now have this interesting thing about we keep putting things into 2 dimensions in space because position is a strong encoding is a really good one, and computation can generate these views through the means of things like distance functions and PCA, stress reduction, dimension reduction, all those things. Cognition, right? We can perceive things that are close together are similar. It looks like there's a cluster. They must be related because they're close by, right? This draws on things from cartography and other things we know about people, where it's just organizationally we like to put things close together that are similar, right? So this is actually a really fascinating opportunity to start to say, this is a medium that seems to work for both the computation as well as for the person. So, how do we actually leverage these two in conjunction with one another? And we should have time, so yes, we will get back to this. Some of the studies that looked at the ability for people to complete intelligence analysis tasks with those text data sets that I talked about, using just the spatial affordances of a large display like this, was also studied, right? That's Christopher Andrews right there. And he ran a study where he found that the ability for people to group text documents, there was nothing fancy about this. It was just text documents in space with a search functionality or something, actually allowed them to offload part of their reasoning into the little groups and the timelines and the other things that they made spatially, similar to how I talked about doing multiplication on paper allows you to offload part of your process onto that visual medium. Really a quite nice study to read about. And a fun display to use. I highly encourage many monitors, lots of pixels. Big displays, way to go. The small mobile stuff, I don't buy it. But, okay. Another analytic technique that we can use is topic modeling, right? And this is a more sophisticated way to generate topics or groups of entities or words from text documents that have some sort of relationship based on their co-occurrence in documents, right? So this is another example of infusing, if you will, another analytic model into that pipeline of raw text to visualization, right? It's no longer just select your words, weight the words, throw those words into your matrix, do dimension reduction, out comes a visualization. Now you have this other technique, which is in the middle of that, to try to generate topics of words that have meaning amongst each other. There are many, many techniques, LDA, LLDA, there are other ones. We won't go through any of them in detail, but I did want to highlight this idea of additional ability to look at topic models of text. Here's a nice example of a system that does this. This is also relative recently. It's called Serendip. by Eric Alexander and others. And what it does is it actually runs a topic model on a collection of, I believe these are historical documents, I believe. And it allows you to visualize the result of a topic model, right? And so you see that each topic here has one column, and the size of that bubble in each column is the amount of relevance that topic has to that particular document, right? So you can start to see things like, oh, it looks like that top document there has a lot to do with the second topic there, but not so much with the other ones, right? And this is another way to give people an overview of really reducing down the dimensionality of your data set in order to give them that overview, driven by the idea that we have an analytic model like a topic model integrated in this case. I believe this is available for download or use online. If you actually look up that paper, they have a link to it. It's kind of fun to play with. I think you can even import your own data, if I remember correctly. Okay, so a fine little detail I talked about there was we are showing the result of a model, right? And remember back to this idea that Google could tell me which house to buy, right? That would be the result of a different kind of model, but nonetheless a result of a model. And there are potential issues that come into play when doing this idea of visualizing the result of a model. And two of the ones that I think have been very well punctuated recently is this idea of interpretability and trust, right, on behalf of the user. So that whole time where I was sitting there saying, oh, and here's a cluster of some documents, and here's the label, and oh, look, we can see that topic 2 is highly relevant to this document, and so on. I saw a bunch of just sort of, nodding heads like this. Well, how do you know that, right? How do you know that's the case? And how do you help a user understand perhaps the uncertainty involved in knowing how much a certain document should be in a certain cluster, a certain document should be in a certain topic, in order to make what could potentially be a very critical decision, right? It's all fun and games if you're thinking about cars and cereals, but there are many serious applications where completely trusting a model or understanding the level of confidence in a model is really, really important. There's a great case study by Jeff Hare's group which showed a little bit of this, and I'll walk you through it because I think it really highlights something interesting, particularly about dimension reduction and that lossiness I talked about. This was done at Stanford, and they looked at the dissertations that were done there, and they did the thing that we just talked about, right? Going from raw text, so dissertations, to words, mapping those into space, into the reduced dimensions, and then plotting them on this particular visualization here, very standard like what we just said. Well, one of the things that comes out was this question of, it looks like, oops, I can't point, but it looks like petroleum engineering is pretty similar to neurobiology over there, right? Because they're pretty close to each other in the general space of this entire visualization. That must mean that we have, a group of faculty that are working together on all of this, right? Because space means similar and this stuff is similar. Well, they had a different approach after seeing this, which is, can I then select petroleum engineering and do a uniform distance to all of the other points, as opposed to this one reduced dimensionality point visualization? And what you get is this, right? Where you start to see that if you actually transform the view based on user selection, you can remove some of the visual artifacts that are involved in the loss that happens in the dimensionality reduction part to go to a single view, right? So here we now see actual distances between petroleum engineering and all other points because a user has told us a selection of a single item that they're interested in. And I forget where neuro whatever goes, but it is not near there, right? Sorry, I don't actually know where it went. Right? And I think this is one example of actually seeing the difference and the skew that can happen, which ultimately sort of leads to some of these interpretability, but also trust issues that come into the dimension reduction versus something that's more focused on a single item compared to all. Right? This is a really interesting case study. I actually worked with some of the faculty that were on these theses committees to understand how they felt collaboration was, and then they compared it to what the visualization showed. And at first they thought they had some massive insight because the people said, wow, there's petroleum engineers working with neurobiologists. We should probably patent stuff, and this is all great, right? But then in reality, that really wasn't the case. It was just an artifact of the particular visualization. Yes?
Can you put the reference back up?
Oh, yes, sorry. Oh, that's actually not a great one. If you look for Jason Chong, interpretability and trust. It was, I forget exactly which year, but I'm happy to provide that afterwards. Great paper. I encourage you. So, aside from some of those issues, generally speaking, right, including machine learning seems to work pretty well. It helps offload the computation. It helps free up the user from the more computationally attractive stuff. But I think we can still do better. And this is where I'm going to go on a bit of a rant. And I always do this when I get to this part because what bugs me about user interaction is when it is used as an easy way out for visual analytic tools, right? It's, when you don't know which model to use for the particular application, you resort to, we'll just put them all in a menu and let the user pick, right? Don't make your problems as a technical visual analytic challenge the problems of the domain experts and the users of your systems, right? User interaction is great to involve users, but please involve them in the right way, right? And so, I want to emphasize this idea of interaction being used to explore data, ask questions, gain insights, right? Not to parameterize your system for ages and ages until you can use something and hope that the person has understood the difference between doing a nonlinear transformation versus a linear transformation, or has chosen the right something or another, and now sees a view and says, well, I guess it worked because it did produce a visualization. When all along, you as the developer probably had a better idea, given the specific domain you're designing for, what perhaps was the better choice to select there. Right? Okay. End of rant. Okay. User interaction is also valuable data, and it can tell us a lot about a person and what they're doing, right? Example of this is a recent study that Eli Brown and others ran. Who here knows how to play Where's Waldo? Come on. The ones that haven't raised their hands can't. Right. So basically, what this study did was it looked at a sequence of user interactions, panning left, right, up, down, zooming in, out, to see how people went through finding Waldo. And we analyzed all of this data afterwards and found interesting patterns that could help us predict, based on sequences we saw very early on, how successful, how fast and accurate somebody would be in the long run, right? And so this is a very basic example of we can model or do analytics on user interaction to gather interesting insights into what people are doing, how well they're doing, what they're trying to find, so on and so forth. Remco Chang and Wenwen also did some work on recovering sort of a more high-level reasoning process from user interactions. So they have this system, WireViz, which I'm showing here, which visualizes the financial transaction data. And what they did is they actually captured all of the interactions that users do with this system. These were professional financial analysts. And then afterwards, they built another system, this one, to visualize all of their interactions, and said, can we figure out what the task was of users at specific times, and map it to the self-reported tasks that users did via Think Aloud protocol while they did it. And they actually had some really nice results here. where they could recover 60% of the strategies, 60% of the methods, and 79% of the findings that those users found, right? So more evidence to suggest that looking at user interactions and the power that they have is a great way to think about coupling cognition with computation. So this leads us to this nice question, which is, can we use the user interactions, right, the stuff that I just talked about, systematically while a visual analytic system is running in order to steer the computation? Because it seems like manually we can do a bunch of math afterwards and find out a lot of interesting things. How do we do that during the time that a visualization is running? And this leads us to an interesting and new area of visual analytics, an exciting area, which is this idea of mixed initiative systems for visual analytics. Who here has heard of mixed initiative systems? Okay, a few of you. All right. Give you a very quick overview before I'm going to dive into some live demos here. Eric Horvitz wrote a paper where he proposed principles of mixed initiative user interfaces. And some of them, there's quite a few, I've outlined here. What it basically comes down to is these user interfaces are ones where there should be a balance between the effort done by the human and the effort done of the system. And this goes into things like tasks. Some tasks people should do, some tasks systems should do. And so on and so forth, right? And there's things here like, consider the uncertainty about user goals. Some interactions may be very hard to understand precisely what the user is trying to accomplish. Others are very good. And so it should be able to do that. It should be able to resolve ambiguity and other things. And the it here is the system that uses this, right? So I now want to talk a bit about how certain systems in visual analytics have started going with this design methodology or design paradigm of mixed initiative systems. The first one to start with is actually probably perhaps the most recent one, Data Voyager. Who here has seen it? All right. Just a few of you. Great. This is new stuff. Good. So this system here was developed by Jeff Hare's group just recently. And it lets people explore visualizations where all they need to do is tell the system what attributes of the data they're interested in, and the system does the rest, right? So thinking about mixed initiative, user select attributes, system generates visualizations, right? And let's look at a demo of this. Let me get out of this thing. All right. How do I, where is it? Data Voyager. All right, can you all see that okay? All right. So here we have, once again, the car data set. And we can actually select attributes that we're interested in. So for example, I might be interested in cylinders and acceleration. Right? And you see by just my selecting of which attributes I'm interested in, the system actually generates a whole variety of visualizations that show me things, right? For example, here is the acceleration and the cylinders, and we generally see that cars that have more cylinders tend to accelerate a bit faster. Right, and other kinds of things. It also, and we can then select these visualizations, make them bigger, so on and so forth. And this is all done in the back end by a model that maps the variables of the data into good visual representations to use, and then says, well, if the user just tells us the attributes that he or she is interested in, the system can start to recommend a bunch of visualizations. This is online, like I said, the link is here. I encourage you to play around with it a bit. For those of you who have your laptop open now, feel free to do that as well, although you might want to just listen to the other ones and just queue those up, right? Because there's a few more like this that I want to talk about. Any questions on this one? There's a lot of details that goes into this about how the system recommends the views and so on. Those details are in the paper. Here, I'll put that back up. In this paper down here, it's a nice system, and it helps illustrate a little bit of this mixed initiative process that we're thinking about more in visual analytics. To generalize out from that a bit, right? Here is the let's just say the traditional, the usual way that we go about it, right? parameters are illuminated to the user in the way of control panels, which, when manipulated, can generate a new visualization. And I think that what we're starting to think about more so is how can manipulations in the visual space drive the change in the parameters of the system, right? So can I tell you 2 points are more similar and have the system figure out which parameters should be adjusted and by how much in order to amplify that similarity that I just mentioned? This circles back to this idea of the semantic interaction pieces I talked about in that one visualization I showed earlier, where we have a set of those principles that basically outline the thing that I just talked about, right? We want to support spatial cognition. We want to let people manipulate those data points in a visualization and have it tell us, have those manipulations steer the algorithm underneath to be able to learn from the similarity that I'm implying. At a technical level, this is what I just described, and with PCA in particular, right? If I move 2 points closer together, what that means is I'm trying to tell PCA to solve for the parallel residual eigenvector versus the orthogonal residual eigenvector when I actually move them apart and show dissimilarity, right? Got a bit technical there for a second, but there is a bit of detail about doing that, and it's really fascinating about what that does to a user interface. Right? So here we have, again, Eli Brown, another one of Eli Brown's work called dysfunction, which does precisely that, right? You can take points in this space, move them closer together or further apart, and have the system compute the weights of the principal components and the dimensions and so on and so forth. So it's just a nice contrast from the IPCA to the current or more recent work of this. And we can also do this for other models, right? We can do it for entity extraction for text. I'll talk a little bit about that. Information retrieval. The next slide, we'll talk a bit about that. But we can start to think about ways to actually let people interact visually as opposed to in these sliders, knobs, buttons, dials, and menus, right? Because the visualization is ultimately where the insight is perceived from. So it may also be a great medium through which questions can be communicated, right? To think about that bidirectionality that we can foster in a visualization. Here's another recent example. It's called interactive intent modeling for information retrieval. It lets people place keywords of search results closer or further from the center of this bullseye-looking thing. And as you do that, it actually gives you different search results because it tries to infer the query that you're trying to create based on you moving these points around in the space. I don't have an example of this one, but yeah. How am I doing on time?
Got 10 minutes.
10 minutes? Okay. In that case, I'm going to skip a few slides. Basically, to some extent, what I was going to talk about was a bit more of the details of that system I showed earlier, the force-inspired semantic interaction, move points around in space. But I'm just going to skip to this particular one here, which is how do we steer entity extraction models, right? So that piece, again, about the entity extraction models that pick up on words that are important and put those into the high-dimensional space. How do I steer those? One of the methods that we came up with is use the highlights that people put into documents as information sent for the models to be much more aggressive about the words that are highlighted, right? So if a user highlights 3 sentences, let the model be much more aggressive about choosing entities from those sentences than it usually would if they're not highlighted. So thinking about that bidirectionality in that sort of way in that example. There's a nice bit of work from some of the PNNL folks that I was lucky enough to be able to collaborate with them on about this active data concept, which is, again, using the spatial representation as a way to let people construct concept maps of their information, where the information is retrieved and shown to them, not only as a result of information retrieval, but also as an inference done on the tasks they're trying to accomplish. Now, before I show the video, is this being shown in any other one of the presentations? Okay. Maybe it will play. Will it play? Whoops. Oh, yes, it was. It's playing, and the sound is really low, so I'll just talk through it, right? So as you can see, people are able to construct spatial representations of their process, and the system, so I move those two things together, actually recommends visualizations and data as a result of doing that. There's also a geospatial component to be able to then map some of these things that are locations directly onto the maps, right? And that was a 30-second preview we usually do for the conferences. But if you're interested in that kind of work, generally what it's trying to do is to infer tasks that people are looking for, things like find relationship between two things and other things like that, and let the system start to mine and compute those things instead of the user find them. If you're interested in that, please talk to Chris, Russ, or Dustin while you're here. I'm sure they'll be able to talk to you quite a bit about that. But again, going after this idea of mixed initiative is really central to that. I want to show another demo, and I'll just switch to it, which is, again, a car data set, right? Where here what we have is your standard XY scatter plot, right? We've got horsepower on one axis, retail price on the other, and lo and behold, it looks like cars that have more horsepower are generally more expensive, right? But this work, done by Hannah Kim, one of my students, and others, is actually an interesting way to let people express cars that you like and cars that you don't like, right? So you can see I can hover over these, and I'll get the details over there. And here's a nice Audi S4, and let's say it's a car that I like. And so I drag it over here into this green box, right? And now, in exploring a bit further, I see a car that I don't like so much. Maybe this thing, a Saturn Vue. I actually don't even know what that is. So maybe that's one that I don't like. So now, in giving the system two training examples of a car that I semantically like and a car I don't like, the system actually computes the similarity function, the linear combination of features, between these 2 points that highlight that difference, right? And it visualizes it in two ways. One is directly in the visual representation, and the other one is this, this sort of bar chart thing down here, which shows me, given the attributes of your data, things like on this one, horsepower, right, is more over towards this side. Cylinder, more over towards this side. And so that actually tells me that the cars that it's found, right, these cars over here are more like the car that I moved over here, the Audi, and these cars over here are more like this one that I put over there. And I can, of course, refine this further, right? I can say, oh, here's another example of one I don't like. I look through here, here's another example of one I don't like. I can look in here and I go, oh, it thinks it thinks all-wheel drive is important. I don't think that's actually that important. I drag it more towards the middle, right? All of the things that you can do to interactively help the system understand your subjective preferences, and in this case, perhaps your domain expertise in a very general way, and use that to train the model to work on all of the data, right? This is a bit of a toy example, but you can start to think about that as another way to do mixed initiative data analytics in a visual way. And this is available online if you want to play with it. It's kind of fun, actually. And actually, oh, this is, yes. You might want to try it, if you will. There are two axes here, and you can do the same thing on each axis. It might be interesting if you and your significant other or spouse are looking for a next car to buy, to map your preference of cars I think we should buy, cars that I don't, onto the x-axis, and his or hers on the other axis. And ideally, you would have a nice 45-degree diagonal. Probably won't happen, but it's a great way to start to think about a very practical use of this particular tool. It's kind of fun. I want to talk about, very briefly, the other end, the far other end of data analysis, right, of the process we talked about. We very quickly said, oh, you go from raw data to your data table, right? And then you do a whole bunch of fancy stuff from there on to get to the visualization. And we've talked about interaction in various places. This particular piece of work called Wrangler is from Jeff Hare and Sean Candell, who have now gone on to start Trifacta. I believe there is the Trifacta Wrangler, which you can also now download for free. But here is what it does, and it's actually quite interesting. It says, assume I have this crime data set where you have reported crimes in different states of the U.S. Wow, that's tiny. I hit Wrangle, and now it shows it to me in this nice little spreadsheet format, right? But oftentimes we want to manipulate this data because we say, look at this. This is terrible. It could report on in Alabama, in Alaska. What I really want is I want this to be its own column, and by the example of me highlighting that particular aspect, it starts to infer transformations in my spreadsheet, right? So it actually says, are you trying to split this column between positions 18 and 25? Are you trying to extract just the word Alabama? Are you trying to split anything after the word in? And I might go, yeah, that's the one, right? But instead of me having to write this transformation or this regular expression to go from a string in this one to a string in that one, observe the interaction that I had to do was to highlight that word that I was interested in, again, in the visual representation that I was actually working in. I can then, of course, say, yep, that's the one, and now I've made a new column in my spreadsheet, which might be cleaner than the original row, which wasn't even a column, that I had beforehand, right? And this idea of data cleaning in a mixed initiative way is a central part of what Trifacta is doing, and it might be something for you all to look at, because it's rarely the case that your data is ready to visualize straight out of the box, right? There's some of this cleaning and munging and merging and disambiguation and deduping your data and some of these other things that you need to do. And I think this is a really nice underexplored area that they're capitalizing on currently. Any questions about some of this mixed initiative stuff that I've talked about?
Have you looked at any of it with, I was just thinking of sometimes with predictive analytics, we can take a simple regression like independence. And you tend to fiddle around with them and see what the most dominant ones are for sensitivity. But there might be certain cases where you do an analysis and you can't get even the values, the independent variables to put in there. But they might be semantically related, or you might be able to put something else in there as a substitute or something you can get hold of. Or if you could do that to the line. I don't know, to say you can weather reading, but you can't get weather, so you put clothes shop sales in there instead. It's a related thing.
I've not looked at that. The idea of switching data variables given the regression or whatever model it is you're trying to understand. No, haven't actually looked at that. That may be another nice one where the user intent or goal could be visually demonstrated, as opposed to you selecting the parameters of the models or the whatever. Right? We are doing some active research on what we're calling visual analytics by demonstration, which is demonstrate visually to a system the analytics and the model and the visualization that you're trying to accomplish, and have the system do all the selection of which technique and the what, right? I mean, it's all that stuff where it's like a domain expert doesn't know that, right? An intelligence analyst might be trained in things like history and international politics, right? Not topic modeling. And a financial analyst might understand, well, I guess currently probably the stochastics of the stock market, which is pretty technical, but maybe not visualization. And I think that really mapping the interaction to the domain expertise is critical challenge for visual analytics going forward. Yeah. Am I on time?
Yeah, you can either speak for another 5 minutes or take 5 minutes questions.
Why don't we do questions, right? I've got a few wrap-up slides, but it's been short enough. I think you all have been attentive enough. I do actually, before, this is somewhat important, let me go through, right, we have a lot of we have a lot of this stuff about human in the loop. There's also alternate theories. One of the ones is this paper we wrote a while back, which is more so human is the loop, right? Where we say that tasks people do computation should map to those tasks, not the other way around, which helps illustrate a lot of this. Some people call it human on the loop. I quite don't know what that means, but every time I think of it, I think of this. And I'm not quite sure whether that's the model we're going for. Regardless, I do want to emphasize that humans should be involved in the computation in some way. I think if not, you just you get to a point where you increase automation beyond people having control and understanding of what's coming out of it, and that's a real danger in society and many tasks within society as well. Bunch of stuff I did not talk about, right, but are still applicable for visual analytics. Cybersecurity, geospatial, storytelling, which I believe is one of Russ's topics. Streaming data, again, I did not talk about that. Image and video, did not talk about that. Analytic provenance, I think this is another talk that we're going to have, which I didn't really mention here. Interaction and display modalities, I quickly said big display. There's also mobile, there's also touch, there's also gesture that you can start to think about. Many, many more really exciting fields, really exciting field that I'd like to keep working on and maybe encourage some of you to work on. I do not want to end without acknowledging the content, where lots of these slides came from. Many graduate students have made almost all of the work here possible, and it wouldn't be possible without them, from many different labs over many different years. The slides here were in large part from slides that John Stasko had developed many years ago, also Chris North at Virginia Tech. And also like to thank you all for your time and attention. I know 3 hours is a lot of listening to do. I think you all have done pretty well at that, and hopefully this will help set the tone for the rest of the week going forward. I think it's a great program, great time to be here, and yeah, thanks. And if we have a few minutes for questions, I'm happy to answer them. Yes?
You mentioned...
Oh, right.
Yes,
Sorry.
You mentioned mapping or getting the user to interact with the underlying data model, things like picking the principal component or the K, the value of K, or whatever it is. Have you done any work transforming that into something that would actually be more useful for a layman, for someone that doesn't understand? So saying, changing this PTA will have this effect. This is how I can transform that into something that you'll understand without losing that ability to actually manipulate on that really base level.
Yeah, so that's not something we've directly looked at. It's interesting though, right? Because what we've done is inverted it and said, well, just show us what you're looking for in the viz, and we're going to hide all that stuff from you, right? But I think there's actually an opportunity to say, how do I make an interface that makes it more meaningful to interact with choosing your principal components, right? More than just a tooltip, but something that might be radically a different design or a different methodology for doing that. We actually have not looked at that. I do know there's interesting work by Mike Gleischer on, he calls it explainers. If you search for explainers visual analytics, it's all about how do we actually make it more, how do we make machine learning more explainable, right? The results that come out of it. Again, maybe not the tuning of the parameters, but certainly how do I make a classifier more interpretable to a person beyond just showing them examples that are in the classifier or not in the classifier.
So it's almost like the distribution on a slider, but for...
Yeah.
I suppose that's the thing that you said you haven't looked at.
Yeah, right, like the distribution on the slider, right. We have not necessarily looked at that. I am considering some interesting things about the physicality of visual analytics and data, right? Like a lot of the stuff that we do now with interactions don't carry any weight, like in the real world, right? You can slide this thing all around all you want, but you have not as good of a feel for the detriment that's causing it, that's to the model. So it'd be nice to communicate the stress of a model to somebody in a physical way. Mm-hmm.
Any other questions? I think you've exhausted them.
All right. Well, thanks.
I
think for the first time I actually feel bad about not providing the whiskey with the glasses. That was fantastic. Thanks, Alex.
Yeah, thank you.